All right, greetings, scholars. Greetings, YouTube. We're continuing our exploration of Chapter 3 on logic from Blitzer Thinking Mathematically. And today we're going to be looking at Section 3.7, Arguments and Truth Tables. There we go with it. A couple of objectives. One, we like to use truth tables to determine validity. And then two, recognize and use forms of valid and invalid arguments. So an argument consists of two parts: premises, the given statements, and conclusion, the result determined by the truth of the premises. A valid argument, the conclusion is true whenever the premises are assumed to be true. Invalid argument, an argument that is not valid, is said to be an invalid argument, also called a fallacy. Truth tables can be used to test validity. So testing the validity of an argument with the truth table. Testing the validity of an argument with the truth table. 1, use a letter to represent each simple statement in the argument. 2, express the premise and the conclusion symbolically. 3, write a symbolic conditional statement of the form premise 1 and premise 2, and until you keep going until you get to premise n. These together imply the conclusion, where n is the number of premises. 4, construct a truth table for the conditional statement in step 3. If the final column of the truth table has all truths, then the conditional statement is a tautology and the argument is valid. If the final column does not have all truths, the conditional statement is not a tautology and the argument is invalid. All right. So in order for an argument to be valid, the final column needs to be a tautology. In other words, the final column needs to be all true. Otherwise, it's invalid. So did the pickiest logician in the galaxy foul up? In Star Trek, the spaceship Enterprise is hit by an ion storm, causing the power to go out. Captain Cook wonders if Mr. Scott is aware of the problem. Mr. Spock replies, if Mr. Scott is still with us, the power should be on momentarily. Moments later, the ship's power comes back on. So if Mr. Scott is still with us, then the power will come on. The power comes on. Therefore, Mr. Scott is still with us. Determine whether the argument is valid or invalid. Okay, let me get some blank paper. So we need this to be slide 8. Copy. Copy. Really not going to let me paste? There it is. Paste. Okay. Let's work with this. Okay. So it says if Mr. Scott is still with us, then the power will come on. So we can let P be Mr. Scott is with us. Q can be the power comes back on. Okay. Okay. So it looks like we have P implies Q and Q therefore P. Okay. Let's see if that works. I guess I should do my graph paper. Okay. So it looks like we have two simple statements. We could say what? P and Q. Okay. And it looks like we have P implies Q and Q. Therefore, all of this together implies P. I think that's how it goes. Let me look at it again. Mr. Scott is still with us, and the power comes on. The power comes on, therefore P. Right? Okay. All right. So let's copy, paste, paste, paste. One more, paste. Okay. Okay, and let's move this over just a little bit. All right, so two simple statements, 4 rows. You should know how to do this by now. True, true, false, false, true, false, true, false. Okay. All right, so based on the way we have it structured, the implication goes first, right? Because that's the nested most set of parentheses. So I'll divide it here. Okay. If this is our column 1, this is our column 2, this will be our column. Now, how did that happen? So undo. This will be our column 3. Okay. So implication is always true except true implies false. So it looks like we're going to have true, false, true, true. Okay. Q, I guess. Okay, so we want to do the and. So we want to say column 3 and column 2. So and is true only when they're both true. Otherwise, it's false. So then we ask ourselves, are they both true? If between 3 and 2, we're going to say yes, no, yes, no. Right? That's our column 4. So then we want to, the final column, we want to say column 4 implies column 1. Implication is always true except true implies false. So we're saying 4 implies 1. True implies true is true. False implies anything is true. True implies false is false. False implies anything is true, right? So then now we can say, okay, is the logic valid? We would say no. Hang on. All right, we would say that this argument is not valid because we didn't finish with the tautology, so the argument is invalid. You could find a case where the antecedent is true, but the conclusion is false. All right, because like what if there was a backup generator, or what if somebody else did it, or what if the power came back on and then something happened to them after the power came back on, right? So let's see. All right, so I think we got the symbolic form already. They got the same. So Spock's argument is invalid or a fallacy. All right, so we got the same thing. Okay. Determine if the following argument is valid. I can't have anything to do more with the operation. If I did, I'd have to lie to the ambassador, and I can't do that. So I think they started with the conclusion. I can't have anything. Let me see. If I had more to do with the operation, then I'd have to lie to the ambassador. I can't lie to the ambassador, therefore I can't have anything more to do with the operation. Okay, I think that's how this goes, right? So, let me see. We're going to let P be I have more to do with the operation, right? So we'll let P be I have more to do with the operation. Okay. And we're going to let Q be I lied to the ambassador. I'm going to abbreviate it as a lie. Now forget it. To the ambassador. I'll abbreviate that. Okay. So again, I think they started with the conclusion here. I can't have anything, right? If I had more to do with the operation, so they're going to have what? P implies Q. We're doing the truth table. P implies Q. All right. And we can't lie to the ambassador. So P implies Q and not Q. So then the conclusion of this is not P. Okay. Kind of been a little bit lazy because I need a copy. I need another blank page. Copy. Paste. Okay. And we don't need, you can get rid of this. You can get rid of all of this. This. Okay. And let's get rid of these, this, and this, and this, and this. Okay. Let's copy this. I'm going to paste it right here. Nope. Paste. No. Paste. There it is. Okay. Paper. I'm going to turn my graph paper back on. Okay. All right. So our two simple statements. So if we start with the innermost nested set, right, that's going to be the implication. So implication is always true except true implies false. So this is going to be true, false, true, true. Which is our column 3. Next, we want to do the not Q. So I'm going to put a bar here. And I'll put one like here, I guess. Maybe to the left a little bit. Okay. And I think I'm actually move this one over. Oh, it's about the same thing. Okay, I can move this one to the side by one and then move, oop, undo. Sorry. There we go. Yeah, that looks better. Okay. Okay, so next let's do the not Q. That's going to be our column 4. So then that's just going to be alternating false, true, false, true. Then we want to say column 3 and column 4, and is only true when they're both true. So we ask ourselves, are they both true? No, 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 and yes. Okay. So that's our column 5. We need to go ahead and do not P. So I'll put a bar, I'll put one here. So the opposite of P, false, false, true, true. That's our column 6. So then finally, we want to say column 5 implies column 6. Implication is always true except true implies false. So false implies anything is true. And then true implies true is true. All right, notice that that's a tautology. Okay. All right. So just to go back real quick, determinant. So is the following argument valid? Based on the way we set it up, we would say yes, the argument is valid because we finished with the tautology. Okay, let's see. If I had anything to do, I'd have to lie. I can't lie, therefore I can't. Right? So I have more to do with the operation. I have to lie to the ambassador. P implies Q and not Q, therefore not P. They finish with their tautology. Therefore, it's a valid argument. Okay. So valid arguments, let's see. A direct reasoning, P implies Q. If P is true, therefore you would conclude that Q is true. the contrapositive, if P implies Q, and if not Q is true, therefore not P would have to be true. Disjunctive reasoning, if you have P or Q and not P is true, then you would conclude therefore Q would have to be true, right? In order for this disjunctive reasoning to be true, at least one of these guys have to be true. And if P is false, then therefore Q would have to be true. And you can do the same with the other, right? If you have the disjunction, at least one is true, and we're saying that Q is false, then P would have to be true. Okay. Transitive reasoning, P implies Q and Q implies R, therefore P implies R. Another way you might see it is not R implies not P. All right, so that's similar to like the law of transitivity. Okay. Fallacy of the converse. When we have P implies Q, and if Q is true, the fallacy is saying that, oh, therefore P is true. But just because the conclusion is true does not imply that the antecedent is necessarily true, right? So that's a fallacy. Of the inverse, if P implies Q, and if not P is true, then the fallacy is going to be that not Q is also true, right? Misuse of the disjunctive reasoning, P or Q. So again, if at least one of these is true, if this is true, therefore this has to be false. Not necessarily. They could both be true, right? Same thing with the Q. P implies Q and Q implies R, therefore R implies P, right? So this is a misuse. This is a false reasoning. These two examples here. Okay. Determine whether the argument is valid or invalid. Identify any sound arguments. There is no need for surgery. I know this because there is a tumor. Because if there is a tumor, then there is need for surgery, but there is no tumor. Let's see. It looks like this is the conclusion again. If there is a tumor, so we'll let P be there's a tumor. Q is going to be a need for surgery. Okay. So it looks like they started with the conclusion. So then it says, if there is a tumor, then there is a need for surgery. So P implies Q. But there now I think before we said when we see but, that's the same as and. So P implies Q and there is no tumor. So not P. Therefore not Q. So I think this one more than likely is going to be invalid, right? Because I think that's the improper use of the contrapositive, right? So let me see. There is no tumor, so we're saying not P. So then these two together implies not Q, right? And this should be a fallacy. This should be an invalid argument. Okay, let me get a copy. Can I just paste? Because no? Okay. This needs to be 19. So let's copy. And come on. You can do it. I believe in you. There it is. Paste. Alright, I think we're good. Okay. Let's get rid of this. And get rid of all the stuff we don't need. Let's get rid of all of this. We can get rid of all of these guys. Get rid of all of this. All of this. This. And this. Okay. So from here, right, we're anticipating it to be a fallacy, but let's do the truth table to confirm or deny. We're going to copy this. paste. Okay. All right. Oh, let me bring my, wait a minute. How do I get rid of that? Let me bring my graph paper back. I'm bringing graphing back. Yep. That's a throwback. Okay, anyway, I'm just a little bit like sleepy and delusional. Okay, let's see. So we're going to do the nested most set of parentheses first. So this will be our column 3. P implies always, implication is always true except true implies false. True, false, true, true. Okay. So then if we do not P, this is going to be our column 4. So that's going to be false, false, true, true. Hopefully I'm doing the right thing. Yeah, I think we're okay. Let's keep going. So then conjunction and is only true when they're both true. So we ask ourselves between 3 and 4, are they both true? No, no, yes, yes. That's column 5. Let's go ahead and do our not Q. So it's alternating what? False, true, false, true, false, true, false, true. That's our column 6. So then we want to say column 5 implies column 6. Implication is always true except true implies false. So we get true, true, false, true. Which confirms our hypothesis or our educated guess. You know, just using our intuition, we felt like the argument was invalid. And this truth table supports our claim that the argument is invalid because the final column is not a tautology. Okay. Okay. Right. Namely because of this guy right here. My dog is a busybody. I think when I get out of class today, I'm gonna take her to a park or something because I haven't taken her to a dog park in quite a while. So she's been like pacing and it's kind of like driving me up the wall. So I need to take her out somewhere, either go walking or something. Darn it, that's annoying. Let me just copy this. Copy. Right here. Paste. Then let's go style. Nope. Yeah, that's fine. Yeah, that was more involved than I intended it to be, but that's okay, right? So because of that false, it's not a tautology, so then we say the argument is invalid. Okay, let's see. So there's a tumor, there's a need for surgery. If there's a tumor, there's a need for surgery. There is no tumor, therefore there is no need. The argument in this form of the fallacy of the inverse, and therefore is invalid. Oh, they didn't even do a truth table. They just used the rule, right? So that's fine. We confirmed it with the truth table, and they just identified which case it was. Drawing a logical conclusion. Draw a valid conclusion from the following premise. If all students get requirements out of the way early, then no student takes required courses in their last semester. Some students take required courses in their last semester, so then what can we conclude? Okay. Let's see. If all students get requirements out of the way early, then no students take required courses in their last semester. So that looks like a P implies Q, right? P is going to be all students get the requirements out of the way early. And then Q is no student takes required courses in their last semester. And then the next premise is some students take required courses in their last semester. So then we would say that's basically what, not Q. All right, so then the conclusion should be what? Therefore. So these 3 dots means therefore. The conclusion should be not P, which is the negation of all is some. Some students did not get their requirements out of the way early. All right, I think that's the conclusion. Looks like we're starting with P implies Q is true and not Q is true. So then therefore the conclusion should be not P. Okay, let's look on the next slide. P implies Q, not Q. Therefore, oh no. The conclusion not P is valid because it forms the contrapositive reasoning of a valid argument when it follows the given premises. The conclusion not P translates as not all students get requirements out of the way early because the negation of all is some not. We can equivalently conclude that some students do not get their requirements out of the way early. All right, so I think that's the way we articulated it. Okay. And we have class in just under 1.5 hours. There's one more section in this chapter, and idealistically, I would like to go ahead and get the next chapter available for you all. But again, the original goal, the initial goal is to finish this chapter by this week, because next week we're going to be starting on another chapter. I might do a bonus lecture that you might not be responsible for. On you all's end, you're really just responsible for whatever I've posted in my open math, right? So I might do an additional section, but you might not have assignments for that, so you don't have to worry about it. So just basically check my open math. Whatever you see there, that's what I expect you to do. All right, scholars. On that note, we're going to end the session here. And from one beautiful mind to another, have a great day. Take care. Peace.